Good morning, everyone. Welcome to Data Visualization with Lab Rat Design. Hope everyone is nice and awake and alert. We're going to be talking about the importance of integrating design within your scientific data and how it is going to be very important for both yourselves and for both the audience as well that will be viewing it. Whether you decide to take that data to publishing or whether it's actually just furthering your own investigations within in-house, as it will give you a clearer perspective of what's going on there. So my name is Ben Jones. I'm the co-founder and creative director of Lab Rat Design. I have personally over 10 years worth of graphic design experience within the design industry, 7 of which is in London, in a marketing and PR agency, and moving to Omaha, I've brought that into the scientific world too. And here is my colleague also.
Hello everyone, my name's Tyler Scher, so I'm a consultant and contributor with Lab Rat Design. I'm filling in for another one of the co-founders, Tim Bilecki. I did my PhD at the Med Center in pathology and microbiology, and I currently do intellectual property at UNMC at the Tech Transfer Office.
So Lab Rat Design is essentially a design service which collaborates with science, so brings science and design together, and we enhance graphics which from data that you provide us from preliminary setting all the way to professional. So, as I said at the beginning, why is design important? Well, we're going to talk about that. And the importance is taking your raw data and actually setting it into a visual form that can be easily seen, and you can easily see trends and patterns, because it's all too common to take the data and to throw various objects on there just to make it look good, and unfortunately that isn't always necessary.
Yes, we have a few historical examples we want to start off with today. Just hoping to emphasize the importance of illustrating your data and of putting some thought into how you illustrate your data as well. So depending on how you illustrate it, you can convey different stories from your data, as I'm sure all of you have at least some experience with. So this is a famous data quartet called Anscombe's Quartet. And you'll note that these data sets, there's around 11 raw numbers on the X and the Y pair for each of the 4 data sets. The sums, the averages, the standard deviations are all nearly identical, if not identical, across all 4 data sets. But there's some outliers, and the outliers aren't, it's not obvious just by looking at the raw data. When we actually go to graph these data sets, you'll be able to see the differences now. So in the first data set, you have a pretty more or less linear relationship, but it's a rough linear relationship, right? There are a lot of outliers. The second data set has kind of a nice curve to it, actually. The third is almost entirely linear, except for one outlier. And then the fourth actually doesn't follow the standard linear relationship at all, but because of that one outlier, actually, it gives you an R-squared value that is closer to linear than you would expect. So it takes graphing. So the point is, it takes graphing these tables of data out in order to actually tease out some of the relationships here in the data. So some more important historical examples as well. So back in the 19th century, the 1850s, there was a cholera outbreak in London. And there was a scientist, John Snow, who, because of using some data visualization techniques, was able to determine what the source of the cholera outbreak was, and able to save a number of lives in that process. So one way to visualize the outbreak here was, and the way that was more traditionally used was actually just documenting deaths per day. So just in a chronological order, just in a big table documenting deaths of individuals due to cholera. That's not overly helpful. So that can tell you some information about the outbreak. It can tell you, how bad it is, how extreme it is, how many people are dying. It can tell you kind of when the outbreak began, and when it's reached its peak, but you can't determine the source just from a table with the x-axis being time and the y-axis being number of deaths, right? So what John Snow pioneered actually was a way to determine the source of that outbreak. So he overlaid numbers of deaths just by these black bars here over an actual street map of the city of London. So he was able, by doing this, he was attempting to determine the epicenter of the outbreak, right? And he highlighted some key locations on the map as well. So in red, we've emphasized the location of water pumps. This is important. So there's 4 water pumps highlighted on this map, and you'll notice that one of these pumps in particular has an increased number of fatalities associated with it. There were a few other outliers, though, as well. So there's a few locations that didn't quite correlate. So, for example, there was a brewery, actually, quite close to this water pump, which we've highlighted now in yellow. So you'd expect the hundreds of workers at that brewery to be also dying of cholera if they were drinking from the nearby water pump. So he had to do some kind of journalism as well and do some interviews, and Dr. Snow determined that maybe, as you would expect, these workers were drinking almost exclusively beer product from the brewery. So they were protected. They weren't drinking water from the nearby pumps. There was another large grouping. So at a workhouse, this employed hundreds of workers as well, but had very little incidences of cholera. And by doing some interviews again, Dr. Snow was able to determine that they had an in-house pump which was separate from the other surrounding wells. So they had their own water supply which was protected. At any rate, a map like this allowed John Snow to determine the epicenter of cholera. And we'll graph kind of, on this next graph, we've highlighted sort of a dynamic illustration of the outbreak, the spread. So you can see, we can probably just play that over and over again a couple of times, but you can see from our red highlights that the largest incidences of cholera are all associated with that center pump, right, on Broad Street. So Dr. Snow was able to determine by graphing the data out visually like this, by taking tables of deaths over time and actually overlaying them on a city map, he was able to determine the critical pump that was infected, the well that was infected, and when he removed the handle to that well and they shut the well off so citizens could no longer get water from that well, he was able to stop the outbreak.
And also to further a little bit more on that is that before even creating this graphic, it was widely perceived that cholera was an airborne disease rather than waterborne. So by creating this, it was then made obvious or made very apparent that it was waterborne.
Yeah, and to further emphasize, the whole field of microbiology was still pretty nascent. And with the limited testing they had, they did do some exploration of the water from that pump, and they weren't able to find particulates or anything that they thought was correlated with the spread of disease. So it was really literally just this correlation of deaths around that area, that geographic area, that was the leading evidence for cholera coming from that pump. So one other kind of critical historical example, this coming from the 1980s in the United States. So this was the Challenger disaster, the Challenger explosion. This was a NASA-led mission that had teachers on board, some scientists on board, and it was a huge disaster. So the rocket exploded, everyone on board died. Importantly, there was a team of engineers who had some data indicating that the testing or the launching conditions weren't going to be optimal for the launch, and That team of engineers at the 11th hour, it was literally 11 p.m. the night before the launch, had just a limited amount of time to convey their message to their administrators and bosses, and ultimately all the way up to the top of NASA, to try to halt the launch. And so their hunch was that the outdoor temperature was going to be too low, and some parts of the rocket, the rubber O-rings, were going to fail. Were likely to fail at those low temperatures. So how could they convey that critically? How could they get that data across at the last hour in order to stop the launch? Unfortunately, they failed in doing that. What they attempted to do was they had a series of 13 tables and graphs that just showed, like this, they showed data just collected from all of their test launches, all their previous launches, their dozens of launches before. But it mixed in was all sorts of additional information that was ancillary. Their main point that they were trying to convey, again, was outdoor temperature correlated with faulty O-rings, with O-ring faults. So why show erosion depth and perimeter affected and all this other information? None of this information is critical to their main message, but it was mixed in with what they were trying to convey. And it didn't let them it clouded the message so they couldn't get their point across. So they did have some illustrations as well, but they were showing, again, they're trying to convey their message in kind of a difficult way. So on some of these rockets, at the top of the rockets, you can see temperature at launch. That's good. They have temperature on there, the O-ring temperature in particular. And then they have this kind of overly complicated code or legend illustrating the damage to those O-rings at these particular test launches, right? So you can either have an S for heating of secondary O-ring, or a B for primary O-ring blow-by, an E and H, or just a empty square for no damage. So it's unnecessarily complicated. And then they did finally have one illustration where they showed, again, using that code, the O-ring damage, along with the temperature of the O-ring at launch time. But they showed this sequentially. So this was their 24 tests, or their 12 tests with 24 rockets. And they instead of arranging these by temperature along the x-axis, they just arranged these by the chronological order of launch. Again, the chronological order of launch here was not important. That's totally arbitrary. It didn't matter what order these rockets were launched in. The important critical data was the temperature at time of launch. So that should have been along the x-axis, right? Temperature. And then along your y-axis, maybe the amount of damage to the O-rings. So then you can really hone in on and fixate on the correlation between temperature and damage. So this is just a really messy way of showing that. On top of that, they really didn't necessarily need to be illustrating these with nice little crayon-looking rockets. That's unnecessary as well. So a few ways to make this a little more helpful that maybe would have allowed them to convey the important message and maybe would have saved lives. One, if they would have arranged their temperature, or their rockets here by temperature. So this is what we've done here. We've arranged by temperature, going from left to right, low to high temperature, and then you can see that there's more, even without knowing what the code is, you can just see there's more scribbles and scratches and filled in squares on the left side of this than there are on the right. And now actually, if we do a better job organizing, not just by temperature, but we actually group the temperatures together. Several of these launches were all done. These are coming out of Florida, so several of these launches are all done at around the same temperature. A lot of them between 60 and 80 degrees Fahrenheit. And what you can see, again, by organizing it like this, is that you start to see damage done to the O-rings at temperatures at around 65 degrees and below. Almost every single rocket has damage done to it at those temperatures. This was going to be the launch temperature, all the way down here, all the way down below 30 degrees. Even at 65 and below, every single O-ring that they had tested at 65 degrees and below had damage done to it. So finally, this is even cleaner. You don't need those rocket illustrations. The critical message here is amount of damage done to the O-rings on the y-axis and the temperature at time of launch on the x-axis, right? And again, you can see a strong correlation here. At basically every launch at 65 degrees Fahrenheit or below, there's some amount of damage being done to the O-rings. And as the temperature decreases, the damage increases. This would have probably, in all likelihood, saved some lives. If the engineers could have conveyed their message with this illustration, with this graph. This again was the estimated the estimated temperature at the time of launch the following day. And you can see if you follow that trend line, there's going to be a critical error down here at these low temperatures.
So just to clarify that all these graphics are from Edward Tufte's book of visualization, which you can see in his examples. And so moving on, we actually have a example from LabRat Design ourselves of conveying that whole idea. One of our clients approached us with a data set of information from gathering blood pressure values from patients visiting their doctors at certain points during a year and certain points in the year too, and how frequently. And they needed to see some sort of trend going on, just furthermore in what we've been talking about. And this is a good example of how it's muddled, and the use of these icons is completely redundant. It doesn't give any value to the design itself, and also by looking at these figures, there isn't a clear trend that can be conveyed here. So we've gone along the same path and redesigned it with new ways of designing it, so you can actually see that there's a clear trend there. We've removed the clutter as well, so there's no need for lovely icons just to make it look nice, and so it becomes this clear, concise piece of data set work. So how can we ensure that good design occurs in our scientific figures? Well, we're going to go through this section right now, and there is a creative director from the Nature publication, Kelly Krause, and she did a very good talk on how to use gold standards in design to convey your data, especially when taking from where you are now, which is in the labs essentially, all the way to publication and trying to get published outside. And so from here, we're going to heavily use examples from her lecture. So she goes along with a four-step process in terms of designing, and this is commonly followed by everyone across the board. This isn't just in scientific research. This is across all areas of design. So when you have your end data and you want to visualize it, there's four key areas. One is which is purpose, and then looking at your key elements, useful context, and then details. So in this example here, we're looking at visualizing the immune response to intestinal antigens. And then the elements within that would be like the animal, the intestines, and then the lymphatics. Useful context would be intact versus leaky lymphatics. And then the details within that are the dendritic cell, inflamed node, and leaky vessel. Now, just to be aware that you do not need to follow all of these points and thoroughly go through them. There may be situations where you may only use two of them, or you may use all of them, and so it just depends on what data you have available and how far you want to take it. So the second stage, when you've outlined the different areas, is to decide what, for lack of a better term, what chart you want to use. Now, that can be anything from like a bar chart pie chart, Venn diagram, all the way to a graphical abstract, like at the other end of the scale. So it can be something very simple, something very complicated. It depends what avenue you want to take and what your end result is, depending on where you're sending your data. And so number 3, the next step is to draw out what you need. And we emphasize, or it is emphasized, that you use a pencil, because you can sketch out what you need and you have the ability to erase it, rather than like drawing over the top and making it look like a mess, basically. But it gives you the freedom creatively as a designer, which you will be. You're now taking yourselves over to a more creative area, and it will allow you to visualize this. And this is a good way of doing it to also convey what you want to your colleagues, as well as maybe a designer in the future. So here's an example that we've created at LabRad Design for one of our clients, and it shows, and it's very primitive. It doesn't need to be detailed. It just needs to show, ideally, what you want on there. And so at this point, this is where your figure will be, and you have like a step-by-step process of taking it from basically preliminary to the end product. And this is in order of priority. So the next thing is making it legible, and then clear, and then attractive at the end. And so this is the final design. After going through the process, you've gone from the sketching with the pencil, and hopefully you will come up with something which is nicely designed. There isn't necessarily going to be as complex as this. Not that this is majorly complex, but certainly if you are in the situation where you want to take your work and have it published, you may ask a designer to create something like this for you. And by going through the sketching process, which I can't emphasize enough, then it will allow that easy communication with the designer there. So moving on for that, we have...
Sorry.
Yep,
yeah,
sorry,
go
ahead.
Previous slides. Do you have the website in a service like that, or will you need somebody to contact you, or do we need to...
We're going to come to that a little later on. So no, that's a legitimate question. Of course, there is. There is tools you can use online that will allow you to plug in data, and you can create charts and various visuals. So you can do that, absolutely.
Yeah, because we have the canvas can be drawn, but sometimes not enough.
Of course.
So you cannot be a little bit creative on it.
Absolutely, yeah. I'll come to that a little later. I could go into more detail a little later. It's further. No. But that's completely fine.
Yeah, please ask questions if you have them.
Yes, of course. But no, that's a very good question. Okay, so moving on from the actual design process there is a whole list of gold standards and best practices within design, and we'll briefly go over them. There's like 1,000,001 different. Even I don't know all of them, and I'm still figuring out them myself. So we will start off with just pure and simply making it very clean, very concise, and very legible. And so here you can see on the left-hand side is a set of graphics, and there's definitely the temptation to make them look good. Throw a gradient on them, maybe make them look 3D, throw some patterns to differentiate them between different areas, stuff like that. A lot of color. And really, when it comes down to it, you don't need that. You're trying to look at your end goal, and what are you trying to do is trying to convey your data as clear as possible to the audience, and maybe the publication too. So on the right-hand side, you can see where that on the left-hand side has been taken and simplified, and there isn't a lot of gradients or anything like that. It's very, very clean, very straightforward, and easily legible. And also another example here is moving away from charts, maybe moving into graphics, where we are using different gradients and different 3Ds, but we're looking at placement. And in the top left, in A, would be the ideal general design, is to make it look very uniform rather than throwing it all over the place, basically, as you can see in B, C, and D here. And here too, as another example of that, but without all the lovely finesse of it looking 3D. So moving on to color, which is a hugely complex subject, but is very important when you are designing your visual data. And a misconception is that moving up and down the color scale is uniform. So when you have a gradient from high to low wavelength, from red to purple essentially, that you move 60 points up, well, if it's down near the green and yellows, then there isn't very much difference in terms of color, versus when you're up in the blues and the purples. So when it comes to designing your visual designing your data, then you need to really be, for lack of a better term, using your eyes and thinking about it. It's not, you're basically taking yourself out of this very constrained scientific, it needs to be 60 amongst the difference between all of them, and now starting to look at it more of where do the colors contrast? Because when you're looking at putting two different values together, contrasting color works. That's how you separate different areas. And so here's an example of that, which you have the red and the black, which are essentially the same, like in terms of density of color, is not very clear. So when you look at it all the way back there, I can barely see the black in there at all. It's a really good example. So an easy solution to that would be to change the background density. Make it less, you can still see it's been highlighted, but you can now see the data within it. And so moving on from that, a big one is color blindness. And there is a larger than what you'd expect population that have some form of color blindness. And we all have a duty to pay attention to that. And so on here, just to clarify, comparing the different one, if you were to look in the top left-hand corner is red, in each of those 3 different types of color blindness, the top left would donate what color they see that red color in, and so forth across all those dots. A simple rule of thumb when designing is not to use red and green together. Like, absolutely not. Use 2 other different colors. You can use red and blue, something like that. But red and green is a really poor combination of colors, because across all forms of color blindness, it becomes confusing on there. So moving on and onto the actual text you use as well. And, I could being a designer and interested in typography, I could talk to you hours about this. However, this will take 2 minutes. So there are 2 main types of design of typography. There is serif and sans serif. You probably already know that. Serif has the embellishments at the end of the letters. Sans serif does not. They also are designed for 2 different purposes. Mainly, serif fonts are used ideally in big blocks of paragraphs. So if you were to open a novel or a book, you'll notice that the text is designed in serif because it leads the eye from one letter onto the other, and it's a lot easier to flow. Sans serif is more titles and headings and the like. So it becomes bolder, easier to see just on the off. So when you're looking at designing your any data interpretation of what you're doing, it's strongly advised you use a sans serif font. And I can give you some examples, which is Helvetica, Arial, or Verdana. And they're available all across Microsoft, Office applications, Adobe, everywhere. So you don't need to purchase them. Try and stay away from serif if you can. I know sometimes they look wonderful, but that's not the idea. And you might get a little confused looking at logos as well. That's a whole different ball game. Don't worry about that. So,
yeah, question.
Did you say stay away from serif for typeface or just overall?
I would say stay away from it overall. If you're doing, when it comes to, that's a very good question. If you're doing a huge block of text, you can use serif, totally. I mean, there's no rules and regulations against it. It's just advice and what is going to be clear to your audience. So if you're doing like a huge block of text, like in a publication where you're reading, serif actually works pretty well. When it comes to the titles and the headers and stuff like that, then sans serif. As a general rule of thumb on there.
So most of what you're going to use in figures would be sans serif.
Yeah.
Yeah.
So an example of serif is like Times New Roman, that kind of thing. Yeah.
Normally for the tables, you usually use an area.
Correct.
So is that also serif?
Oh, yes. Serif, no, sans serif is
That's
Arial.
sans serif. Yeah, Arial, Helvetica, and Verdana.
Yeah. So when you look at the font, if you see on here any of these embellishments, like on the edges, that's considered a serif font. And then when it's just straight cut, like on the right-hand side without anything, sans serif. I can do another lesson about this, like another time. We'll just take everyone's evening, it'll be great. Coffee, beers, the works. Okay, so moving on with text, we have how you display them in graphs and charts and the like. And remembering that we, as human beings, like things to be convenient. Like it's not pleasing on the eye to make people do work when coming to looking at visualizations. And so it's very tempting to have text at an angle and trying to make it work in that respect in terms of what constraints you have in the space and such, and try and stay away from doing angular text if you can. So there's an idea here. Versus, so just more over on here is that you have a standard bar chart. Well, moving on from that, a nice alternative is to change the way your charts are. If it doesn't fit within the area constraint you have, then try and move it around a little bit. But try and keep the text either vertical or horizontal. It makes it a lot easier for people to read and to see which bar it's actually referring to as well, which is important.
Yeah, so just by converting the bar charts from vertical bars to horizontal in this case, allows you to then have your labels horizontal, much easier to read. The bars are pretty easy to intuit or visualize, either vertically or horizontally, but the actual font, much easier to read horizontally.
Totally. So bringing that all together, now we've talked about the design process and the gold standards within design itself. We have some examples here.
Oh, yeah. So this is maybe a typical illustration that we would see in cancer biology, for example. So this is a lot going on in one illustration. Not only do you have three sort of different groupings or cohorts of data, you also have four different pathways being represented by these individual small circle colors as well within your three different groupings. This can just be, so on the left you have over 40 individual sample sets. On the right you have over 60. And you can just see how cluttered and how difficult it is to actually intuit or grasp any message from this. It looks appealing, it looks pretty, I guess I should say, but it's hard to actually get any information out of it. So just by reorganizing the data, so instead of having this Venn diagram with your three different data sets, if you actually separate those out into pie charts with three different colors, that makes it a little more easy to see the groupings within your data sets, both within the breast and the colorectal. Breast being on the left on top, colorectal on the bottom. On top of that, instead of having smaller circles individually colored, again, some of these colors now, again, are using red, yellow, green. These are kind of no-nos that can be difficult for some of your audience to be able to differentiate between those colors. Instead, you could do what we did over in B on the right, bottom right. You can actually separate out those 4 different pathways, and then correlate by color in the pie chart again what number of individual data sets are represented in each of those 4 pathways. So it may not look as pretty, but it's much easier to actually get information out of that organization. It still looks very clean. Much cleaner, actually. So crafting a message. So again, it's important to think about what story or what's the purpose, what's the point you're trying to convey with your data. So you start off with raw data on the top. You can separate out those raw data sets into 3 different ranges, going from 0 to 30, 31 to 60, 61 to 100. You can still keep them in the order they were collected, and just represent those by size of circle now. Now, if you want to actually begin to organize those in order from smallest quantity to largest quantity, you could represent that data now with columns or with bars, going again from 0 to 100. Still with the same 3 groupings, however, now just with size of bars. And then this allows you, in the bar chart, allows you to then be able to clearly see any sort of significance between your sample sets here. So this is just kind of conveying, again, ways to think about how you want to organize your data based on the message you're trying to convey. This is another example of some sloppy data organization or a representation. So this is something that I've definitely been guilty of, just kind of taking random sort of icons. So circles, triangles, stars, and then using random colors that to me seem to easily differentiate between the 3, but there really isn't a rhyme or reason, I don't think, to why this individual picked these 3 icons and these 3 colors to represent this data. This just looks messy, very messy data. So you have 3 different icons again, different colors. You also have some of these icons circled. What exactly does that mean? Why is that important? So one way to clean this up would actually be to just simplify, just make it easier. Let's keep the same general icon. Let's keep it a circle, or pick all triangles, but just pick one of the 3. You don't need 3 different icons in there. So if we pick circles, now you can have large circles for your pseudogenes, the processed and the non-processed, large red, large black. Your genes would be small black circles. And if they're transcribed, if your pseudogenes are transcribed, you just fill in the circle, either filled in red for transcribed pseudogene or filled in, or for processed, or filled in black for transcribed non-processed. So that makes it a lot more easier now to intuit. You don't have to do code breaking in order to figure out what's trying to be conveyed in this illustration.
So just to jump in and just to clarify, these are examples from Michael Korinsky, and we've got a bunch of other resources on our resource page on our website too. So moving on to online tools, which is something you should definitely take advantage of. You won't necessarily have the Adobe Creative Suite, and so, which costs a fortune, actually, as a designer, and especially if you're only using it once in a blue moon. So, but we have a big, a long bank of free resource, well, not necessarily free, but open source resources that you can go online and take advantage of, both in guides and tutorials, tools, and data visualization examples. So you can certainly get some more information there. And actually, I'm going to show you a example right now. So bear with me. So this is our resources webpage, and here you have all the, especially here at this point, all the links here to different resources in terms of like color generators for palettes and hues and stuff like that, all the way to charts and other ways of visualizing your data. So one of the examples is plot.ly, and so you'd go on, and as I said, not all of these are free. Some of them you have to pay for. They're not that much. There are some free ones on there. So if you go on here, here's an example of putting in your data in the top middle area here, and then through toggling with the different options down the left-hand side, and in the middle you can create different charts and different visualizations. And, excuse me, here's an example of a previously created one here. So, and these are available online, and you can download them and use them either digitally or in print too. And so, moving back. Yeah, so that's, as I said, that's all available at labraddesign.com. You can go on there and they're all available for you.
I think you mentioned it, Ben, but what would be, again, what would be a good resource or two for color, for picking out either your palette or hues?
Hold on, I can pick that up for you right now. So for that would be going down to Color Brewer.
Okay.
Would be a good one on there, or the Color Palette Generator. The palettes are very strong, actually, because they have had thousands and thousands of different entries in terms of data collection over the internet in different designs. So if you're looking for a particular look and feel of your data, you can look at that palette and just use all the colors on there. Okay, so moving on is we just want to show you some examples that we've encountered ourselves at Labrad Design, just tying in everything we've been talking about together to show how it works with some of the clients. And this is an example that we've collected from one of our clients requiring a graphical abstract, and you can see how it's not a polished, finished design, and it shouldn't be either, but it's enough that we could take from it and we can design on there. And this is the final design that we came up with on there. But it's just emphasizing the fact that as scientific researchers, the importance of sketching down your design and not necessarily, you don't have to have it finished. If you're communicating with a designer or a colleague, then you can take that further. And here's another example from one of our colleagues too, not colleagues, client even. And another graphical abstract was required here, but we actually decided to take it in a different route. This looks far too messy for the data to be conveyed to the audience. And at a pinch, you want to see what's going on, so we actually pushed for a more 3D design to show what the data was actually showing there in that respect. And then this was a design created. We had some information given to us by a client, and then we created it ourselves. We sketched it out. Oh, actually, I think it might have been our client. I'm sorry. And then creating another design from that too on there. So you can see the power of sketching before just diving in and creating your visuals. You can make changes, and it's very, very powerful. And as I said, using a pencil is key also. And one more example here of another sketch done with all the data, and then the final design here. But by no means don't think that you need to have something as polished and as elaborate as what we're showing here. This is just examples of what we've done, the things that you can do with the free tools and resources that we have online on the website. You can create very, very powerful charts and graphs and the like to be able to move forward with that. So quickly just going over the last section, which is the future of scientific graphics. Everything's very digital at the moment, and animated GIFs, very popular, obviously. And so a foresight that we can see is moving, especially digitally, is animation, which is going to be the next thing. We do not expect, I'm going to tell you, it is not expected of you guys to be doing animation at all. But it is an option which you're now moving into, and it's something that will be really encapsulated into your audience. And here's another example that we created also for a client here. So rather than it being a static diagram, maybe over 2 or 3 parts, you now have moving animation, which is very engaging to your audience, both scientific and non also. And that concludes our presentation. Do you have any questions? Thank you.
Thank you. If you have any questions about resources, for example, or tools, we have another example over here as well of augmented reality as a future means of conveying your illustration, your graphical point. So if you want to come up and use an iPad, we have a few examples of that up here as well.
Yeah, that's it. Go forth and sketch and design and make beautiful drawings of your data.
Okay.
Okay, thank you.